Hello, welcome to Chapter 5, Section 1, Using Transformations to Graph Quadratic Functions. I'm going to do the final example, the application problem. However, there is something that I left out of the previous video that I need to talk about first. And it's kind of a summary of what we've done so far, and it'll be useful for when we do the application problem. So I'm going to put that in here. That's why it's blank. That's the actual sheet. Okay? Here's what we've seen before. We have seen these. This is from Algebra 1. If I do y subtract y sub 1 equals slope times x subtract x sub 1. This is called point slope form. And again, this is from Algebra 1. We, in Algebra 2, we have not talked about this yet, but this is something that you should know about. This comes from the formula for slope. Now, in the classes where I teach Algebra 1, I tell them to write this instead. I move this minus y sub 1 over to the other side. So I get y equals slope times x minus x sub 1 plus y sub 1. And this x sub 1, y sub 1, I can actually write it this way. The subscripts cause problems. So instead of this, I'm actually going to use this. Now that throws off my Algebra 1 students. They're like, why did you switch that? However, you guys are used to that now. You've seen this before. And where have you seen this before? This is linear functions. You guys have seen it with me with absolute value functions. Because absolute value functions, we see this. Y equals a times the absolute value of x minus h plus k. So I switch the m for slope with this number, but both times you're multiplying. But the form is the same. The only thing is, instead of just subtracting, not only do I subtract, but then I take the absolute value. This is called vertex form. So it is reasonable, but not entirely correct, to say that slope-intercept form, when you convert it, move that over that side, is actually vertex form for linear functions. The thing is that linear functions don't have vertices, okay? But the form is the same, which is a really cool idea in math. If the form is the same, then we can learn about new things that have the same form, even if it's about something completely different. That's a mind-blowing proposition. Now you're probably wondering, yeah, but aren't we doing quadratics? Well, check this out. For quadratic functions, it looks like this. So linear functions is to the first power. Absolute value function, I just take the absolute value of it. Quadratic, I take it to the second power. Mind blown. This is actually also called vertex form because parabolas have a vertex. So it allows me to know how far left or right it moved and how far up or down it moved. Now we've already done this in the first problems because we let a equal 1. And we did some other stuff because we did vertical and horizontal translations in the second video, the second example. But now we're tying it all together, okay? So I wanted to get that out there and talk about vertex form. Let's do the problem for this example. All right. You're not going to like these numbers, but that's because Dr. Berger got them for real. The minimum braking distance measured in feet for a vehicle on dry concrete, so no wet concrete, which would change things, is approximated by distance based on velocity. See how the d and the v actually tell me what we have. 0.045 v squared where v is the vehicle's speed, also known as velocity. Velocity means speed in a direction. Okay, so there's a little bit of physics there, but at this point you guys haven't had physics, or most of you haven't had physics, so it'll be okay. We can interchange them. All right, so that is distance based on velocity is 0.045 v to the second power. It's a quadratic function. Now, if the vehicle's tires are in poor condition, so they're a little bare, a little bald, the braking distance then becomes d with a little tiny subscript p for poor of v equals 0.068 v squared. Those are not nice numbers. What kind of transformation goes from this one to that one? And what does the transformation mean? Okay, in vertex form, this is 0.045 v minus 0, because v minus 0 is v squared, plus 0. So my vertex is actually at the origin, 0, 0. Same thing with this one, 0.068 times v minus 0 squared plus 0. So it's not a translation. Nothing, this stayed the same and that stayed the same. It seems like it's either a stretch or compression. So my question is, what do you multiply 0.045 by to get 0.068? All right. I'm not proud. 0.068 divided by 0.045, and I get 1.51 repeating. Math 1, let's change that to a fraction. 68 over 45. Okay. So it looks, I was just double checking something. It looks like it's approximately 1.5. Okay, I'm sure there's been a rounding error because this is the whole thing, right? So that means that this function is multiplied by 1.5 to get this function. And when you multiply by 1.5, that is a vertical stretch by 1.5. And what does it actually mean? The vertical component, if I graphed it, remember, my independent variable is the velocity, my dependent variable is the distance. That means it takes 1.5 times as many feet to stop. So if it was able to stop in 10 feet, then it was able to stop, it would take, with bad tires, it would take 15 feet. If it was able to stop in 200 feet, with bad tires, it would take 300 feet, multiplied by 1.5. Okay, we'll see you with the guided practice problems.